everything that we're doing today, yeah, you guys get to be the recorded class today. Last time it was 7th period, and it didn't go well, as you heard. But then I wasn't here, and so I was like, oh no, they have to watch this one. What?
You're recording right now.
It doesn't matter. I know. It's just so that if I can put it on my website, that way people
Fred
can watch
Lanningham, forever.
is here this morning.
Forever in notes.
Yes, there you go. All right, so, and I don't try to do anything extra fancy, but.
Oh, hey, Fred.
Hey. Okay, so in chapter 14, every question in this entire section, the questions are all the same. And the question is, calculate the pH of this solution. The difference is what's in the solution and the process that you go through for calculating the pH value, whether it's strong acids or bases, or weak acids or bases, or if it's combinations of the two to calculate that final pH. And so really in the notes today, all I'm going to go through and do is, a bunch of examples that involve different combinations of things in the solution and how you go about calculating the pH. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8 examples, but some of them are short. We're going to start easy, and we're going to start by calculating the pH of strong acidic solutions. The first thing you need to remember is if it is a strong acidic solution or a strong basic solution, that you should recognize that that means that basically there is 100% dissociation, maybe not quite 199 point something. Basically, most of the molecules break apart and ionize, okay, which is important in figuring out concentrations. And the other thing is, if all of these questions are asking us to calculate the pH, on Wednesday, I gave you guys the equation for calculating the pH, and it is what? Negative log of the hydrogen ion concentration. By the way, same thing as saying hydronium ion concentration, okay? Those things are interchangeable, and they mean the same thing. And so if all of these questions are going to ask me to calculate the pH value, then I need to know the hydrogen ion concentration. So that's going to be what you're looking for, and the way you find that is going to be different depending on the situation. And then pretty much you're ending all of the problems by negative logging something to find the pH. Okay, so first thing here, calculating the pH of 0.1 molar HNO3. That's nitric acid. Okay, I already told you these are all strong acidic solutions, these first examples here. And so if you have 0.1 molar HNO3, since HNO3 is a strong acid, that means that it completely breaks apart into hydrogen ions and nitrate ions. If my concentration of nitrate is 0.1 and it completely breaks apart, that means after it completely breaks apart, I've got 0 left of HNO3. All of it has turned into H plus and NO3 minus. What would be the concentration of H plus after this completely dissociates? What would it be? You can think about it. You do not need to, for strong acids, set up an ice table, okay? But we'll do it for right now, just so you can see what's going on. If I start with 0.1 here and 0, 0, and I subtract x to give me 0, because 100% dissociation leaves me with none of this. And then I have plus x. What does x equal? 0.1 minus x equals 0. X equals 0.1. So I have 0.1 here and 0.1 here. So then my hydrogen ion concentration is just 0.1 molar. Okay? So, you can do that if that helps you. You have to recognize that since it's a strong acid, you end up with 0 of this left at the end, and all of it turns into hydrogen and nitrate ions. This is your concentration. It's the same as the concentration of the acid is. So as long as you only have one hydrogen, it's always going to be the same number if it's a strong acid. So then you can just negative log that number, and it gives you the pH. and the negative log of 0.1 is just 1. And significant figures, base it off of what you were given. So there's 2 significant figures there, so really this answer should be 1.00. Because remember, on Wednesday, it's the numbers after the decimal in pH values that count as significant figures. Okay? Next one, HClO4. Perchloric acid is also strong. If I have 1 times 10 to the negative 10th molar of hydrochloric acid, what's my concentration of hydrogen ions? Yes, 1 times 10 to the negative 10th. pH is the negative log of that. 1 times 10 to the negative 10th. What is that answer? I mean, plug it into your calculator if you need to. It's something that you can probably do in your head if you remember log stuff, but you get a pH of 10. What is the problem with that? It is not acidic. You should always pay attention to what pH value you get and what you're looking for. I'm looking for an acidic pH. This is definitely not 1. Okay, here's the thing. This concentration, 1 times 10 to the negative 10th, is super tiny. There's like hardly any perchloric acid molecules even in that solution. It is mostly just water. And so just a rule that you need to pay attention to, which is why I did this as an example, is if the hydrogen ion concentration is less than 1 times 10 to the negative 7, then the pH is just equal to 7. It's basically a neutral solution because this concentration is so tiny. It doesn't affect the pH at all. It's almost like it's not even there. So just look for numbers that are smaller than that. If it's smaller than that, there's not enough of it to make it actually very acidic at all. So it's neutral. All right, for the next example, we're going to take a couple things, we're going to mix them together, and we're going to figure out what the pH is of the resulting solution. So I'll let you write this down, but we've got HNO3 solution mixing with HCl. Okay, what I'm doing in this problem is I'm taking 2 separate solutions and combining them together into one. So I'm going to take my 54 milliliters of 0.00125 HNO3 and I'm going to dump those 54 milliliters into a beaker, and then I'm going to take 25 milliliters of HCl and I'm going to dump it into the same beaker, and I'm going to have one solution of all of those mixed together. Now both of these are strong acids, and so they're both going to fully dissociate. So when I put them in the solution, I'm going to have hydrogen ions from the nitric acid, I'm going to have hydrogen ions from the hydrochloric acid, and then there will be chloride ions, and there will be nitrate ions, just kind of all floating around in there. What I need to figure out is what's the concentration of hydrogen ions, and it's coming from 2 sources, the nitric acid and the hydrochloric. So first of all, since these are both strong, if I have 0.00125 molar HNO3, then that means I have 0.00125 molar hydrogen ions that come from that. And if I have 0.025 molar HCl, then that means I have 0.025 molar hydrogen ions after it breaks apart. So I have these concentrations of hydrogen ions, but they're in their separate solutions. So I can't just simply add these together to get the total hydrogen ion concentration because the volume of the solution changes, which affects the molar concentration of stuff. So I have to think about what the total volume is. So it'd be my 25 milliliters plus 54 milliliters, and that's 79. And what I have to do is figure out what is the new concentration of hydrogen ions for each one of these situations in the 79 milliliter solution. So for each one, I have to do M1V1 equals M2V2. So for the HNO3, the initial molarity is 0.00125. The initial volume is 54 milliliters. And then I'm looking for what's the molarity after the volume changes to 79 milliliters. Okay, I calculate that M2 value, and it is 8.54 times 10 to the negative fourth. Okay, that's my first hydrogen ion concentration. And now I have to figure out what's the new hydrogen ion concentration for the hydrogen ions that came from HCl in 79 milliliters. So I do the same thing. For HCl, M1V1 equals M2V2. Okay, for M2, when I calculate that and plug in everything for HCl, I get 0.00791. That's the hydrogen ion concentration. So I can take those two numbers and add them together to get my total hydrogen ion concentration. When I add those numbers together, I get 0.00876. What do I do with the hydrogen ion concentration to get pH? What do I do? Negative log 0.00876. And that gives me the pH is 2.06. Okay, so you've got to figure out the hydrogen ion concentration separately after the solutions combine before you can add the hydrogen ion concentration together and negative log it. Does that make sense? Any questions before we go on? All right, so we've done strong acids, pH, calculating the pH of strong acids. We've done calculating the pH of a solution when you mix two strong acids together. Now, calculating a strong base is pretty much the same idea. There is one tiny thing that is different at the end when you do your calculation. Sodium hydroxide is a strong base. Now, the strong bases, and you have to recognize these. When they ask you to calculate pH values, you have to recognize if they're strong or weak because it affects how you do the calculation. Strong bases are alkali metals, hydroxides, so lithium through cesium, not francium. Any of those combined with a hydroxide would be a strong base. And then on the alkali earth metals, it's calcium, strontium, and barium that count as strong bases. So sodium hydroxide is a strong base, which means it fully dissociates, which means it's going to break apart into hydroxide ions and sodium ions. And I'll have 0.25 molar of each one. Okay, so what you can do is if I negative log 0.25, that gives me 0.60. Is that the pH? On all the previous ones, I just negative logged the concentration and it gave me the pH value. Why is this number not the pH? Yeah, in order to get the pH, you have to negative log the hydrogen ion concentration value. Here what I did was I negative logged the hydroxide ion concentration value. So that doesn't give me the pH, it gives me the pOH. How do I get the pH from this number then? Could subtract it from what? 14. Okay, so 14 minus this number. This is just the added step, is if you have a hydroxide ion concentration, that's okay, you can negative log it, but it gives you the pOH, and so you have to subtract that from 14 to get the actual pH. And so again, since we're dealing with something that's basic, you should definitely have a pH that's greater than 7. So always double check on that, because some people will just kind of get through the whole problem and then just negative log it and be done. But it's basic, so the pH can't be 0.6. You got to subtract it from 14. Okay, so that's the added step right here when you're dealing with bases instead of acids. All right, next. All right, this is the fun stuff. This is where you get to use ice tables again. And that is calculating the pH of a weak acid or a weak base. I think on page 637, I have that page number written. I think they actually write down like a list of steps for you to follow. We're just going to go through those steps in examples. The reason why calculating the pH of a weak acid is different than a strong acid is because weak acids don't fully dissociate. And so you can't just take like whatever the concentration is and assume that that's your concentration of hydrogen ions, because it's definitely not, because it doesn't fully dissociate. There's only going to be a small, tiny percentage of it that breaks apart. So what you have to figure out is you have to figure out what is the concentration of hydrogen ions, and you're going to do that by basically setting up an ice table and solving for X and doing all of that to figure out your hydrogen ion concentration so you can negative log it to get the pH. So acetic acid is HC2H3O2. Okay, when we set this up, it is in water, and if you wrote the water over on the reactant side, it would be correct, okay, just like we talked about with the homework. But really all that matters is the dissociation of this. And so it's going to break apart, some of it, only a tiny bit of it, into hydrogen ions and acetate ions. And these are all in solution. They give you the Ka value, which is the equilibrium constant for the dissociation of especially weak acids. So before the dissociation, the acetic acid concentration is 0.250 molar. And 0 and 0 over here, plus X and plus X. And over here I have minus X, and then I get 0.250 minus X. What I want to do is I want to solve for X, because that will give me the hydrogen ion concentration, which I can then negative log to find the pH. So in order to solve for X, you've got to put it into the equilibrium expression of products over reactants and set it equal to the K value, which is 1.8 times 10 to the negative 5. That's going to give me, or that's going to be equal to my products will be X times X, so that's X squared, over my reactants, which is 0.250 minus X. And you have to solve for X. So you guys have done this before, and some of you forgot to do this on your quiz, but when you have a K value that is so small that means your X value is also going to be so small that if you're subtracting it or adding it, what can you do? Cancel it out, make it 0, okay? So you end up with x squared over 0.25. And then that becomes a lot easier to solve for x. You just have to multiply by 0.25 and then square root it. Or you could put it in your solver and get your x value. Okay, x, when you calculate that, gives you the hydrogen ion concentration, which is 2.1 times 10 to the negative 3. So then if you negative log that, it equals your pH. And that would give you 2.67. Okay, so if it's a weak acid or a weak base, there always has to be the ice table set up, and you have to solve for X to get the concentration that you would negative log. For this one, I'm gonna change it a little bit because I typed in a whole new problem just to answer this question, what is the percent dissociation? And instead of having to start over, we can just use what we already did. Another application of weak acid questions, pH questions, would be to calculate the percent dissociation. And so we're just going to do this based on the example that we just did. If they give you all of this information and they say, what is the percent dissociation? What they're asking you is how much of the acetic acid molecules, what percentage of them actually broke apart. So how can you figure that out? You can take your value for X, which is the 2.1 times 10 to the negative 3. And we're going to divide it by what the concentration would be if it was 100% dissociated. 100% dissociation would give me 0.250. So basically, what's your X value over what was the starting concentration? And then that'll give you a decimal that you multiply by 100, and that'll give you a percent. It's usually a very small percentage. So, I mean, when we're dealing with weak acids, it's usually less than 3%. A lot of times less than 1%. So that means out of all of the acetic acid molecules, only 0.84% of them actually break apart and ionize into hydrogen and acetate ions. Okay, so that will be a question you have to answer about weak acids as well. We're almost there. Any questions on that? Okay, let's do... we're going to skip another one here. I skipped number 3, so you can make this one number 3. Okay, so we've done pH values of strong acids, pH values of weak acids, pH values of strong bases, and then when you combine strong acids together. So now I am combining acids together again, except for it says, what is the pH of a solution where I've got 25 milliliters, and I want this to be 25 as well, not 250. 25 milliliters of 0.25 molar HNO3 mixed with 25 milliliters HNO2. HNO3, that's nitric acid. That's a strong acid. HNO2 is weak. So in the first example where we combined things together, we had two strong acids. And so we had to add all the hydrogen ion concentration together. And when you have a situation where you have a strong and a weak being mixed together, what happens basically is that the strong acid, I put the strong acid wins, but basically the strong acid is the only one that matters, because the majority of the hydrogen ions in that solution is going to come from the strong acid. The amount of hydrogen ions that comes from the weak acid is so tiny that it is not going to affect the pH at all, so you don't need to calculate it. You could, but you would just be doing extra work for yourself to get the same answer because it would be so small. So the strong acid is HNO3, so 0.250 molar HNO3 means 0.250 molar of hydrogen ions. Can I just negative log 0.250? You kind of want to, but the thing that you do need to pay attention to is that I'm mixing those two solutions together. So even though the amount of hydrogen ions that comes from this doesn't matter, the volume changes, and so it changes this concentration. So you've got to do the M1V1 equals M2V2 to solve for the new concentration. So it'd be 0.250 times 25 equals M2 times 50, and then M2 would be 0.125. That would be the concentration of hydrogen ions that you would negative log to get the pH value, and that's 0.903. Okay. I just have one more example, and it is calculating the pH of a weak base. And the only reason why I want to do this on here, the process is the same as far as like you've got to set up an ice table and solve for X and do all that. But I want you guys to see the setup of the equation when you're dealing with bases versus acids. It's a little bit different. And this is the last one. All right, by the way, on this one, number 4, if you're dealing with bases, it's the same rule. Like if you're combining a strong base and a weak base, the strong base is the only one that matters, but you have to take into consideration the volume change. Okay, I've got an NH3 solution. You should always recognize NH3 as basic. That's what a common one that you're going to see a lot. So when I have NH3 in solution, when you're dealing with bases, with acids we kind of leave off the water even though we know it's there because we just deal with the dissociation of it. With bases, it's helpful to draw out the water molecule as HOH so that you can show the hydrogen comes over here from the water and you get NH4 plus, and then you have OH molecules as a product as well. Now I'm looking for the pH. So in this case, I don't have hydrogen ions concentration that I can find, but I can find hydroxide ion concentrations. They would also, by the way, give you not a Ka value, but a Kb value. What do you think the B means? It's basic, okay? It's the same thing as a Ka value. It's just when you're dealing with bases instead of acids, it's products over reactants, not liquids, so water would be left out, you know, of the ice table. But they would give you a Kb value for this, and there are charts in your book to look them up if they're not given to you. So the Kb value for NH3 is 1.8 times 10 to the negative 5th. So you set up an ice table exactly the same way. So you have 0.25, 0, 0. 0.25 is my given. So plus X, and minus X over here. Okay, so I can set up my products over reactants equal to the Kb value and solve for X. So 1.8 times 10 to the negative fifth equals x squared over 0.25 minus x. I won't go through the solving for x. We've done that. That's x is 0.0021. That's your hydroxide ion concentration. Negative log that gives you 2.68. Is that the answer? No, what do I do with that number? Subtract it from 14. This number is my POH. Why? Because I negative logged the hydroxide ion concentration. So then I have to do 14 minus that number to get the pH value. And it's 11.32.